let's talk about the elephant in the room. I'm very disappointed that none of you have mentioned how awesome my shoes are today. Your exam grades were largely pretty darn great. Our section average was an 82. The other two sections were in the 60s. So we have crushed my enemies. So I'm pretty darn jazzed about that. Realistically, if you have yet to crack a 50 on either test, you should highly consider not being here anymore. If you have passed one test but did very poorly on the other test, then you need to have a hard look at your study habits and all of that kind of stuff, because the material for exam 3, I would say that it's in between the difficulty of the material on exam 1 and the material that was on exam 2. It's a lot of the same techniques that we covered on exam 1, but it's going to be using complex numbers and all of that kind of stuff, which largely is just learning about how to use your calculator as efficiently as possible. But anyway, I would say that exam 3 is somewhere in the ballpark of between exam 1 and 2 in difficulty. So it can still bite you in the ass, as it were. If you pass both exams, then obviously you're doing okay, so keep on trucking. If you want to look at your tests, shoot me an email to schedule an appointment, because I have like 115 advisees to deal with over the next 2 weeks. So I don't have like real office hours. It's just everything is by appointment only. All right, so let's cover stuff. So today is largely going to be a math review. Should be a review. Some of it might be new to you guys. We're going to start off by talking about complex numbers. And then I'm also going to go ahead and review sinusoidal signals today, just because if I don't, I will talk literally forever on Friday. All right, so let's start with complex numbers. So the first thing that I'm going to do here is I'm going to put a complex plane in the center of my paper. I'm sure Ashton is having flashbacks. So I want to talk about that in a moment, actually. So here I have a 2D graph kind of thing. And effectively, the horizontal axis is the real number line that we all learned about in like the 3rd grade, right? So we have positive numbers on the right-hand side, negative numbers on the left-hand side. Everything is nice and neat and all of that kind of jazz. And then our vertical axis is where imaginary numbers live, okay? So this is also just a number line, but it's shifted by 90 degrees. And that's literally all the imaginary thing means, is that there's a 90-degree phase shift between the real part and the imaginary part. So in context, that's literally just the difference between a cosine function and a sine function is a 90-degree phase angle. That's all that the imaginary numbers literally represent, a phase shift of 90 degrees. There is nothing remotely scary or intimidating about that. It's just saying, instead of using a cosine function as my frame of reference, let's use a sine function. That's it. Okay. All right, so there are multiple different ways that I can choose to represent a complex number, okay? So I'm going to start over here on the left-hand side with a rectangular form complex number. So in rectangular form, a complex number, let's call it capital A, and I'm putting a bar over it because I am incapable of writing in bold. So in a textbook, you would typically see a complex number represented by a bold-faced variable. Because I can't do that, I put a bar over my complex numbers. And I'm going to call this A plus JB, where the real part of complex number A is lowercase a, and the imaginary part of complex number A is lowercase b. So think of this as just a two-dimensional vector. We're going to move A units in the real direction and B units in the imaginary direction to form our complex number on the complex plane. So it might be something like this, right? So this might be complex number A, and the projection of A onto the real axis is lowercase a, and the projection of A onto the imaginary axis is lowercase b. So it's exactly a two-dimensional vector. We're going A units in the x direction or the real direction, B units in the y direction or the imaginary direction. Okay, so nothing scary or intimidating about this, hopefully. Now, another way that we can represent a complex number is in exponential form. I'm regretting how large I made that graph in the middle, but we'll make it okay. So in our exponential form, we are going to be dealing with the complex number, but instead of looking at it in terms of a real part and an imaginary part, we're going to be looking at it in terms of a magnitude and a phase angle. Okay. So our complex number A has a length, which I'm going to denote as the absolute value of A, and that literally just means the magnitude. Okay. So we're also going to have a phase angle, which I'm going to call theta A. So in exponential form, my complex number A would look like the magnitude e to the j theta A. Now, before I go any further here, I'm actually a little bit perturbed with you guys because not a single one of you has asked me what the hell j is. That's pretty important. So somebody asked me what the hell j is. Patrick.
What's J?
What's j? Thank you for the question. Okay. So way back in your math classes, probably even as far back as high school, you learned that I was defined to be the square root of -1. Well, in electrical engineering, I is current. So we can't use that letter. So being as lazy as electrical engineers are, we said, hey, let's call it lowercase j. So it is literally just the same thing as the square root of -1 or the I that you dealt with in your math class, but because we use I so often for current, we can't use it here. So everywhere you see j, just treat it like square root of -1 or I from your math classes, and you're good to go. So while we're on the topic of j, we can actually make a little table here in the middle that'll help us remember some things. So let's start here in the middle of this table with j to the first power. Okay, so j to the first power is obviously just j, or the square root of -1. J squared is then the square root of -1 squared, which is -1. J to the third power is j squared times j to the 1. So this is actually just -j. J to the fourth power is j squared times j squared. So that's going to look like +1. J to the fifth power is j to the fourth power times j to the first power. So that's just going to be 1 times j. So we're back to j. And it just cycles that way over and over and over again, right? Going in the opposite direction, j to the 0th power, well, anything to the 0th power is 1. J to the negative 1 is 1 over j. If we multiplied that by j over j, we're going to get j in the numerator and negative 1 in the denominator. So that's going to look like negative j. J to the negative 2 is just j to the negative 1 times j to the negative 1. So that's going to be negative j times negative j. So that's going to be positive j squared. Well, since j squared is negative 1, that looks like negative 1. J to the minus 3 is j to the minus 2 times j to the minus 1. So that's negative 1 times negative j comes out to be positive j. And it's literally just cycling in the exact same pattern as before, right? So realistically, we only ever actually need to know j to the 1, j to the 2, j to the 3, and j to the 4. Everything else we can get by just subtracting 4 from the index until we get into the range, subtracting 4 or adding 4 to the index until we get into the range of j to the 1 through j to the 4, and then we know how everything works, okay? The reason why I'm mentioning this is because some of your calculators can only handle, I think, j to the 0 or j to the negative 3 through j to the positive 3 or something like that. The Casio 991s, at least the white ones like this, can do j to the whatever. And I'm pretty sure the Casio 115s and the TIs can only handle to the plus or minus third power. So you have to correct it by understanding how it cycles. Anyway. All right. So we've talked about j. We have our exponential form complex number. Over here on the right-hand side, I'm going to try to sneak this in, is our polar form representation. Okay. So the polar form representation of a complex number is the exact same information that is in the exponential form of a complex number. However, it's just a shorthand notation. So in polar form, we would represent this same complex number as the magnitude of A, angle operator, theta A. Now, let me make a note here. I'm going to just put an asterisk over here, or a star or whatever on the left, and a star over here on the right. These stars are indicating that these are the forms that your calculator can handle, okay? So your calculator can take complex numbers in rectangular form, and they can take complex numbers in polar form. They cannot take complex numbers in exponential form. So if you're ever given an exponential form, put it in polar form by keeping the magnitude, keeping the phase angle, and throwing the e to the j bit completely away. Does not matter at all. All right, so now let's talk about how we go back and forth between these two forms, okay? So let's start by figuring out how to go from rectangular form into exponential form. We have effectively a right triangle here, and so we can just use very simple identities to figure out what our magnitude will be in terms of our rectangular components and what our phase angle will be in terms of our rectangular components, right? So the magnitude of A is simply going to be the square root of lowercase a squared plus lowercase b squared, or in a more formal way, the real part of A squared plus the imaginary part of A squared. This is literally nothing more than application of Pythagorean theorem. The magnitude here is the hypotenuse of this right triangle. A and B are the not hypotenuse legs. Nothing remotely fancy whatsoever going on here. Our phase angle theta A can be found in a few different ways, but my preferred way is the inverse tangent or the arctangent of the imaginary part over the real part. Now, in a moment, we're going to work an example kind of messes with this relationship, and I'll explain what I mean by that in a moment, okay? But before we do that, now that we know how to go from rectangular into polar or exponential form, let's talk about how to go the other way around. Basic trig identities, right? So A will just be the magnitude of our complex number, capital A, cosine theta A, or in other words, the real part of A is just the magnitude of A cosine theta A, and B is just the magnitude of A sine theta A. And so the imaginary part of any complex number is determined by simply taking the magnitude of the complex number and multiplying that by the sine of our phasor. So here's how we go back and forth and all of that jazz. So what I'm going to do now is I'm going to introduce you guys to a very simple example problem. And it is going to show you why having a good calculator is amazing. Which is also why I talked about you guys getting rid of your peasant calculators at the beginning of the class and upgrading to the TI 36s or the Casio 115s or the 991s. Okay. So very simple example problem. I want us to express the complex number x is equal to -5 plus j8 in polar form. That's it. So the magnitude of complex number x should just be the square root of -5 squared plus 8 squared. So that's 25 and 64. I'm too lazy to do that in my head. Square root of 89. That can probably be simplified, but I'm not going to bother. The angle of complex number x is the inverse tangent of the imaginary part, which is 8, divided by the real part, which is -5. Throwing that in my calculator, and I'm going to have my angle given to me in degrees. I get -57.995 degrees. So all I have done here is directly apply the relationships that I literally just told you. Every single one of those is correct. Why is this answer wrong? Right. So let me articulate what Mr. Wagasback, I believe, Daniel, is saying. So if I were to plot the rectangular form of x, so here's my real axis, and here's my imaginary axis. I have a negative real part and a positive imaginary part. So loosely, it's somewhere over here. Okay. According to my polar form representation, it has a magnitude of the square root of 89 and an angle of negative, let's call it 60 degrees. So down here. Why does this happen? Well, our calculator literally cannot tell the difference between the inverse tangent of 8 over negative 5 and the inverse tangent of negative 8 over positive 5. So effectively, if the rectangular form is telling us that it lies in quadrant 2, our calculator is telling us it lies in quadrant 4, and that's a limitation of our calculator's inverse tangent function. Because the inverse tangent function is always going to give us an angle between positive and negative 90 degrees. So that answer is always going to be in quadrant 1 or quadrant 4. Now, we can correct this by just adding or subtracting 180 degrees, because that's just going to move us halfway around the unit circle. Literally doesn't matter which one we do. However, I fundamentally believe that that is a pain in the ass that I'm not willing to deal with. So instead, the calculators that I've suggested that you guys use can literally automatically convert a rectangular form number into a polar form number, and it will always get it correct. So learning how to use your calculator effectively and efficiently will be the key to not having just tons of small, weird phase angle errors all over the damn place. Okay. So I'm going to talk you guys through how to do it. Let me see if I brought my Casio 115. So what's the most popular calculator in this class? Is it the 991 or is it the TI? Yeah. All right, we'll do the TI first, then we'll do both of the Casios. Okay. So my preferred calculator for complex number math is the TI. And the reason is you don't have to actually change the mode of the calculator at all, which we'll see you have to do with the Casios. And it's incredibly easy to store variables in the TI. It's not particularly difficult to store variables in the Casios, but for the TI, it's just really, really simple. So for this particular problem, I would type into my TI 36 -5 plus 8, and then I'm going to press the pi button 3 times. That's going to give me my imaginary operator I. And then I'm going to press second and then the pi button, and that brings up my complex menu. That second pi button is where all of the complex number math stuff lives, okay? So the first option is how we get the angle operator for polar form. Option 2 returns the polar angle of a complex number. Option 3 returns the magnitude of a complex number. Option 4 converts a complex number into polar form, which is exactly what we're trying to do. So I'm going to go with option 4, and it's going to spit out 9.434 with an angle of 122.005 degrees. Well, I'd be willing to bet that the square root of 89 is that 9.434 bit. And this angle of 122.005 makes a lot more sense for our actual angle because it lies in quadrant 2. right? So that's how we can do that conversion with a TI. Option 5, for those of you that are paying attention, is to go from polar to rectangular. And I have all of my calculators set up to have it return the value in polar form as the default. You don't have to do that, but I can show you how to do that later. All right, so that's how you do it on a TI. Now let's talk about the Casio 991. Okay. So turning my calculator on, first thing I'm doing is I'm pressing the menu button. So that's the button to the right of the, I don't know, 4 directional arrows or whatever at the top. And then I am going to option 2 that says complex. So that's me putting my calculator in complex mode. So this is the main drawback, in my opinion, of using a Casio for this complex number math, is that you have to remember to put it in complex mode, and then you have to remember to take it out of complex mode to do any other simple math. And I'm lazy and I don't like pressing those 2 or 3 keys to get there, okay? So now that my calculator is in complex mode, I'm gonna type in that -5 plus 8. And then to get my imaginary operator I press the engineering key, ENG, okay? Just as a heads up, to get the angle operator for polar numbers, I just press Shift ENG. So both the imaginary operator I and the angle operator are found with the engineering key. One of them is the normal engineering key, the other one is Shift the engineering key. Now for the Casio 991s, if you press the option button here, which is on the top left, that's what brings up your menu of all of the complex things that you can deal with, right? So we have the argument operation, which returns the angle. The conjugate operation we'll talk about here in a moment. We can get the real part, the imaginary part. If we scroll through the second screen, option 1 converts into polar, option 2 converts into rectangular. So I press the option key, I press the down arrow once, and then option 1, and it should look like a little triangle, and then R angle operator theta. Pressing equal, I get square root of 89 with an angle of 122.005, blah, blah, blah. Same thing. Okay. Now for the Casio 115s, similar, we press the mode button, which is to the right of the 4 arrow keys in the middle. Press option 2 once again for complex. Type in -5 plus 8. Press the engineering key. But the Casio 115 does not have an option button. Instead, you have to press Shift 2 to get into the complex menu. And then it's pretty similar to the options that are available in the Casio 991s. So we have the argument operation, the conjugate operation. Number 3 is converting to polar form. Number 4 is converting to rectangular form. So I'm going to press option 3 equals, and once again, I get square root of 89, angle 122 and change. Okay. So I know I went through that pretty quickly. If any of you guys have any questions after I finish lecturing about how to use your calculators, I am more than happy to answer them. But we have something. All right, so now let's talk about doing math with complex numbers. And I want you guys to understand that I don't actually expect you to be able to do practically any of this by hand. That's what calculators are for. However, we will be using some of these things as identities later on to explain why things work in particular ways. So that's mainly the purpose of why I'm explaining how the math works to you. Okay. So let's start with an operation that is specific to complex numbers, which is the complex conjugate. So once again, here in the middle, I'm going to draw a complex plane. Here's my real axis, my imaginary axis, And I'm going to give myself the complex number A, like so, whose real part is lowercase a, and whose imaginary part is lowercase b. And I need to put a bar on top of that A. In polar form, we would have the following magnitude and the following phase angle, right? So if A is lowercase a plus j lowercase b, a conjugate, which I'm denoting with that asterisk, is simply A, but I change the sign on the imaginary part of the complex number. So if I had A plus JB, A conjugate is simply A minus JB. Okay. So all the conjugate operation does is effectively flip our complex number over the horizontal axis. So down here would be A conjugate. The projection of a conjugate onto the real axis is still just lowercase a. The projection onto the imaginary axis is now negative b. Now let's talk about what the conjugate operation looks like for polar and exponential form complex numbers. So if complex number A is a angle theta A, what do you guys think A conjugate is based on our graph? Did the magnitude of the complex number change? Not at all. The angle is now just negative. Absolutely correct. So, just to recap here, to perform the complex conjugate operation on a rectangular form complex number, we change the sign on the imaginary part of the complex number. To perform the complex conjugate operation on a polar form complex number or an exponential form complex number, we just change the sign on the angle. Same exact thing. Okay. Bless you. All right, so before we move on to normal mathematical operations, does anybody have any questions, comments, or concerns regarding the conjugate operation? Okay. So now let's talk about simple addition. So let's say that I have a complex number, capital A, that is A plus JB, and a complex number B that is C plus JD, like so. If I want to add these complex numbers, that's going to give me A plus JB plus C plus JD. And this works effectively just like adding vectors do, right? So we're going to add the real parts together, and then we're going to add the imaginary parts together. So this would look like A plus C plus J B plus D. That's a difference. Not particularly difficult. There is not any easy or straightforward way to do addition with polar form complex numbers. So realistically, if you had polar form complex numbers and you wanted to do addition by hand, you would need to convert those polar form complex numbers into rectangular form complex numbers and then do this. Calculator does not care, by the way. It can add, subtract, all that kind of stuff, rectangular and polar form complex numbers with no problems. All right, now let's talk about subtraction. So subtraction is just addition, but there's a negative sign involved, right? So using the same complex numbers, A minus B is going to look like A plus JB minus C plus JD. And so this is going to look like A minus C plus J minus D. Again, nothing particularly difficult about the subtraction operation. So unless anybody has any questions, I'm going to move on to multiplication. All right. So multiplication is where things are going to start to get a little bit annoying in rectangular form, but it's not going to be too terrifying. So if we have the same two complex numbers that we've been dealing with, I want to multiply these numbers together, and I want to make a little note about this. When I put two complex numbers next to each other, what I mean by this is multiply those two complex numbers. Okay, so let me talk about why I can't put a cross in the middle, like a standard multiplication sign. You might accidentally interpret that to mean take the cross product of these things because they are very vector-like. They're a two-dimensional vector, so the cross product operation literally doesn't work. Okay. I can't put a dot in the middle because you might confuse that to be the dot product operation, which does not exist for complex numbers. I can't put an asterisk in the middle to imply multiplication because you might confuse that with the complex conjugate operation. So literally, the only option I have that is clear is put one complex number next to another complex number and hope to God you guys remember that that means multiply. Every other thing that we commonly use to denote multiplication might accidentally mean something else. So I'm never going to put any of those things down. Okay. When you see one complex number next to another complex number, that means you are multiplying. So here, we're going to have A plus JB times C plus JD, like so. And now I'm going to FOIL this out like, I don't know, 5th grade or 6th grade or 8th grade math, whenever the hell you FOILed out polynomials. And this is going to look like A times C plus J, A times D, plus J, B times C, plus J squared, B times D. Now I'm going to group this together in terms of real parts and imaginary parts, right? So A times C is obviously real because there's no J's involved. And J squared, B times D, is also real because J squared is just -1. We've already discussed that. So this is going to look like AC minus BD is the real part of our result, plus J AD plus BC is the imaginary part of our result. Now, that is a little annoying. So let's look at what happens if we use exponential form complex numbers to do multiplication. Right? So over here, let's say that I have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of B, e to the j theta B. Multiplying these two together is going to give me the magnitude of A, e to the j theta A, times the magnitude of B, e to the j theta B. And what's going to result from this multiplication is that I will have the magnitude of A multiplied by the magnitude of B. And what happens when I multiply exponential together? They add. So this is going to look like e to the j theta A plus theta B. So multiplication of polar form or exponential form complex numbers is really easy because we just multiply the magnitudes and add the angles, call it a day. In polar form, this is going to look like magnitude of A, magnitude of B, angle, theta A plus theta B. So here's multiplication. Anybody have any questions, comments, or concerns about this? All right. And lastly, we will do division. And this is a real pain in the ass in rectangular, but it is going to accidentally introduce an identity for us, which is why I'm bothering to do it. So once again, oops, I don't need those signs. We're dealing with complex number A and complex number B. Oops, and that should be C. Yeah. So if I divide these two complex numbers, this is going to look like A plus JB divided by C plus JB. Now, there's not anything particularly wrong with this. However, in every other operation that we've dealt with, the result of my operation yielded a distinct real part and a distinct imaginary part, and we do not have that anymore. So let's talk about how we're going to fix that. And so I'm going to multiply this ratio of complex number A over complex number B with a very odd looking form of the number 1, okay? So that odd looking form of the number 1 is going to be, anything will write, B conjugate over B conjugate. So I'm just going to multiply this fraction by C minus JD over C minus JD. Let's look what's going to happen at the denominator first. Okay. So I'm going to have C squared minus J CD plus J CD minus J squared D squared. We know that negative JCD plus JCD, those guys cancel each other out, right? And what is negative J squared? Positive 1. So in our denominator, this is actually just going to look like C squared plus D squared. So what we just found out, I'll do this in blue, is that complex number B multiplied by complex number B conjugate simply gives us the magnitude of B squared. So now that our denominator is literally just a number, right? It's a real number. C squared plus D squared is going to be a real number. Let's look at what happens to our numerator. What happens to our numerator is going to be really similar to what happened with multiplication, right? So we're going to have A times C minus J A times D plus JB times C minus J squared B times D. And so that's going to look like AC plus BD plus J BC minus AD. And all of that is over C squared plus D squared. So what I'm going to do now is I'm just going to split that up. And we can now easily see that it has a distinct real part and a distinct imaginary part, like a rectangular form complex number should. So, like I said, a bit of a pain in the butt, but definitely not impossible by any stretch of the imagination. We just have to multiply by complex conjugate over complex conjugate. So effectively that multiplication is just making the denominator real so that we can split it up and distribute it between the real and the imaginary part. In exponential form, this division is much more straightforward. Magnitude of A, e to the j theta A divided by magnitude of B, e to the j theta B is just going to look like the magnitude of A divided by the magnitude of B, e to the j, all right, that should be positive J, theta A minus theta B. So we divide the magnitudes and subtract the phase angles, which is exactly the opposite of multiplication. In polar form, this will be magnitude of A over magnitude of B with an angle of theta A minus theta B. And this is where my lecture on the review of complex numbers ends. Okay, so this is all I'm expecting you to be able to do. And 99% of this, I'm expecting you to do it with your calculators. So for the in-class assignment and all of that kind of stuff, do write something down so that the graders know you're doing stuff. That being said, the expectation is that for the in-class assignment, you're learning to use your calculator to perform all of these operations. Yes, sir. I don't know. I don't know what's going to come out if you store something in your calculator in complex mode and then get out of complex mode and try to recall that variable. I have no idea what's going to happen. Yeah. Yes. So very, very loosely, I'm not trying to jump too far ahead. So the next topic that I'm going to talk about literally today is a review of sinusoids, okay? So the reason why we're going to be talking about sinusoids is because electricity in the industrialized world is distributed using sinusoidal voltages and currents. Okay, that's what AC voltage and current means in the context of the electricity grid and all that kind of stuff. So all of the outlets around the classroom and all that kind of stuff are actually providing some sinusoidal voltage, roughly 169 volts peak value. Its frequency is 120 pi radians per second, and its phase angle is whatever the hell it is when we started measuring it, right? As it turns out, doing math or doing circuit analysis with all of those sinusoidal functions is an absolute nightmare. And I'm going to prove that to you guys on Friday by working a very simple example problem containing just a voltage source, a resistor, and an inductor. And it will take me about 25 minutes to go through that one problem using our sinusoidal signals. However, a complex number, particularly a complex number in polar form, carries the same information as a sinusoidal signal. It has a specific magnitude and it has a specific phase angle. And it turns out that doing all of the math with complex numbers turns all of the calculus and trig relationships that are horrifying into simple algebra. So that's why we're going to use complex numbers. So, like I said, I'm going to review complex numbers here in a moment. I'm going to work a very simple example problem that will hopefully scare you away from ever trying to do circuit analysis in what I'm going to call the time domain, because it's completely and utterly asinine. And instead, we are going to work in what's called the frequency domain, which is using complex number representations of everything. So it'll come together by the end of Friday's lecture. Bear with me ranting about math for 2 days. All right. So now let's talk about sinusoids. So unfortunately, you guys are going to have to deal with my inability to draw a sine function worth a damn. Okay, so they're always going to be lopsided and they're never going to look nice and even. Hopefully you'll be able to catch what I'm throwing. So here I'm making a plane. Just for the sake of argument, let's say that this axis is voltage as a function of time. And this axis over here is time. Okay. And now you have to watch me draw this shittily. What you for? All right, so here is a sinusoidal signal, right? Let's call this VA as a function of time. And there are actually two different ways that we can represent this sinusoidal signal. Okay. We could represent it as a cosine function. So as a cosine function, this might look like Vm cosine omega t plus some phase angle, theta v. Or we could represent it as a sine function, which would be Vm sine omega t plus some phase angle phi. So what I want you to take away from these mathematical representations here, and we're going to talk our way through things, that constant term that's outside of the cosine function and the sine function is the same for both. The coefficient that's being multiplied by time t, omega, is the same for both. But our angle at the end, theta v and phi v, are different angles. Okay. Now let's talk about what all of those different constituent parts mean. Okay. So the first thing that we're going to talk about is Vm. So Vm is the amplitude of the sinusoidal signal. All it represents is the distance between the horizontal axis and the peak value. And it could be the positive peak value or the negative peak value, it's literally the exact same distance. Okay. So this is effectively just the size of our sinusoid measured from 0 to its peak. Okay. Should always be expressed as a positive number. Okay. So if I have a sinusoid with an amplitude of 5 volts, that means that it's cycling between positive 5 volts and negative 5 volts over and over and over again as time progresses. Okay, so that's all Vm means, just the amplitude of our sinusoidal function. Okay. The next thing that we're going to look at is omega. So omega is the angular frequency of the sinusoidal signal. And it always has units of radians per second. So angular frequency is literally always measured in radians per second. Okay? It will never not be that. I want to be very, very specific about that, because if I ever accidentally forget to give you the units, those are the units 100% of the time. Okay? So now let's talk about where we can see this or how we can determine this from our graph. Okay. So the angular frequency really represents how quickly our oscillations are occurring. So if I draw a dashed line down from our positive peak here and another dashed line from the next positive peak, the distance between these two dashed lines is capital T, where capital T is the period of the sinusoidal signal. And it's simply the amount of time it takes for one cycle to occur. Okay. So when you guys were in your engineering, probably 121 class, I think, at least back when I used to teach it, you guys had to learn about pulse width modulation signals and all of that kind of stuff. And you learned a relationship between period and linear frequency F. Okay. So period is typically measured in seconds. Linear frequency F, so F is the linear frequency. Signal, and it's measured in hertz, where a hertz is just 1 per second. Right? So the period T is the time it takes for one cycle to occur. Our linear frequency F is the number of cycles that occur in 1 second. So T and F are the inverses of each other, right? So T is equal to 1 over F. Well, angular frequency and linear frequency are related to each other because there are exactly 2 pi radians in each cycle of our sinusoid. So we can say that omega is just 2 pi F. And from this, we can see that omega is just 2 pi over our period, or our period is just, I think I had that backwards. I think it's 2 pi over the omega, because 2 pi radians divided by radians per second will give us seconds, yes. So 2 pi over omega. I have to apologize for that. We'll do that. So this is how we can determine our angular frequency from a graph. If we know what the period is, because we can see when the positive peaks occur, or when the negative peaks occur, or when the zero crossings that are increasing occur, or whatever, as long as we're looking at the same point on 2 different cycles, we can figure out what our period is. If we know the period, we now know how to get our angular frequency. Okay. So the last thing that we need to talk about then is our phase angle. Okay. And this is probably the most difficult part of this to understand. So theta v and phi v represent the phase angle of their respective sinusoids. So let's talk about what that phase angle means. Realistically, it's just an indication of a shift in time of our signal. Okay? So what I mean by that specifically is when we think of a cosine function, when does its maximum value occur? 0. But up here, I have a function that's represented as a cosine, and its maximum value doesn't occur at t is equal to 0. It occurs at some later point in time. Well, that later point in time is related to the phase angle. What is, so when does a sinusoidal function, so a sine function specifically, when does that equal 0? Typically at t is equal to 0 as well, but we can see from a sine perspective that it hits 0 at some point before t is equal to 0, which is why we have a phase angle for our sinusoid. So our phase angle is just a way to represent how much our signal is shifted in time about our horizontal axis, okay? So let's call this distance, so the amount of shift we're seeing from the horizontal axis to this peak, let's call that delta t. Okay. Our phase angle, theta v, is just going to be omega times delta t. But we have to pay attention to what the sign of the phase angle is. Okay? So whenever we have a phase angle, or excuse me, whenever we have a signal that's shifted to the right, we have a negative phase angle. Okay. We call this a delay running out of room there. So that's why it's negative. So we're indicating that we're delaying the signal by some amount of time with a negative phase angle. So its positive peak is occurring later in time than it would if our phase angle was zero. Whenever our signal is shifted to the right, excuse me, to the left, our phase angle is positive. And we typically call this advanced because it's hitting its peak value earlier than we expect it to. To me, at least, this always seemed kind of backwards. Okay? Like a positive phase angle in my head, my first thought is always it should be shifted to the right because positive numbers are on the right side of the number line. And something that's shifted to the left is have a negative phase angle because the negative numbers are on the left-hand side of the number line. But we are looking at our signal as a function of time, and time is increasing from left to right as we go across our graph, okay? So everything to the left of zero is effectively the past. Everything to the right of zero is the future. So if we're shifting it to the right, we're pushing our signal into the future, which means we are delaying when it starts. If we're shifting our signal to the left, we're effectively pushing it into the past, or we're advancing when it starts with respect to time t is equal to zero. Right? So I understand that it can be a little bit confusing. It still trips me up sometime, and I'm a jackass that's been doing this for far too long, okay? Yes. Yes. So, well, when we're dealing with a cosine function, sure, okay? So let's talk about that really quickly here, right? If we view this signal that I've drawn up here as a cosine function, our phase angle will be a positive, shit, I got it backwards. Our phase angle will be a negative number because as a cosine function, we see that it's hitting its peak value at a time later than t is equal to zero. However, if we choose to view this as a sine function, it would actually have a positive phase angle because it's hitting zero at a time before t is equal to zero. So it all depends on whether we're looking at the signal as a sine function or a cosine function as to how we interpret what that phase angle means. So for a cosine function, I always look at when the peak is occurring because I'm used to seeing the peak occur at t is equal to zero. For a sine function, I always look at when it's crossing zero and increasing because that's usually what happens at t is equal to zero for a sine function. Is that? Bless you. Right. So if I chose, for instance, to say that this amount of time was delta t, what I'd wind up getting is a negative phase angle that is greater than 360 degrees because it's including all of a cycle and then a little bit more. And because 360 degrees and zero are the exact same angle, it's still going to be technically the correct answer. We'll actually talk about that in a moment when we talk about leading and lagging. Ashton, why did your face do that? Oh, sure. All right. So these are the basics of sinusoidal signals, what all the different parts mean, and all of that kind of good stuff. As part of our job as electrical engineers, sometimes we have to compare sinusoids to each other. And so I want to talk about what that process looks like a little bit, and I think that'll be the last thing that we'll talk about today. So generally speaking, there are three basic rules that we need to follow when we are comparing sinusoidal signals to each other. Okay? The first rule is that all signals must be expressed that C got away from me exclusively as sine functions or cosine functions. Now, I am going to tell you that in this class, we will always be dealing with cosine. And the reason specifically that I am choosing to deal exclusively with cosine functions, meaning that every sine function is going to get converted into a cosine function, is from what we saw earlier when we were looking at polar form complex numbers and how to put them back into rectangular form. So the real part of a complex number is the cosine of the angle part. And so since we're going to be dealing with real signals, we always want to be dealing with cosine functions, okay? Because sine functions are what's taking care of the imaginary part of it, okay? So let's say that I had a signal. Let me do this in red. So if I have a signal VA of t and it is 10 cosine 20t plus 18 degrees volts. And I had a second signal, VB of t is equal to 8 sine 20t plus 65 degrees volts. I would need to convert that sine function into a cosine function, okay? So unfortunately, we're going to have to throw some trig identities, okay? So I'm going to go way down here on this page, and I'm just going to start putting trig identities down, okay? You can put them wherever you want to in your notes. But these are trig identities that we are going to wind up applying over the next few days. And I misspelled identities. So the first trig identity is that sine of omega t is the same as cosine omega t minus 90 degrees. Meaning that if we want to convert from a sine function to a cosine function, we simply subtract 90 degrees from the phase angle, whatever phase angle we have, okay? While we're at it, we can go the other way around, and we could say that cosine of omega t is simply the sine of omega t plus 90 degrees. So subtract 90 to go from sine to cosine, add 90 to go from cosine to sine. Come back up here. So from this, VB of t would just be 8 cosine 20t minus 25 degrees volts. Nothing particularly difficult about that. We now have both signals expressed as cosine functions, so we could compare them. But we have a couple of other things that we need to pay attention to as well. So our second rule for comparing sinusoids is that all signals must have a positive amplitude. Meaning, if we had a third signal, VC of t was -5 cosine 20t plus 15 degrees volts, we would have to figure out how to get rid of that negative sign out front. So there's a trig identity for that as well. So negative sine omega t is simply positive sine omega t plus or minus 180 degrees. Does not matter if we add the 180 or we subtract the 180 because we're literally getting the exact same angle. And similarly, negative cosine omega t is equal to positive cosine omega t plus or minus 180 degrees. I typically want my resultant angle to be between positive 180 and negative 180. So the smallest possible magnitude of the angle. So that's how I choose whether or not I'm adding or subtracting 180 degrees. But it literally does not matter. If you always add 180 degrees, you're still right. If you always subtract 180 degrees, you're still correct. Literally does not make any difference whatsoever. Okay? So for me personally, I would wind up subtracting 180 degrees from this guy because I know that if I add 180 degrees, I'm going to get a number that's larger than 180, which is not the smallest possible way to represent that angle. Okay. So this would look like positive 5 cosine 20t minus 165 degrees volts. My mental math is correct. I think it's okay. Thank you, Josh. All right, and then our last rule is that all signals must have the same frequency. So they all have to have the same angular frequency, or they all have to have the same linear frequency. Okay? There is no trig identity that fixes this. If they don't have the same frequencies, we can't really compare it. Okay? So now let's look at what that comparison looks like, which is a topic called leading and lagging. And if you thought phase angles were confusing before, you're going to be even more frustrated here. So I'm going to try to make this as small of a pain in the ass as possible while acknowledging that it is absolutely a pain in the ass. Okay. So I'm going to use those exact same signals that I just talked about a moment ago, right? So VA of t was 10 cosine 20t plus something, right? 18. The B of t was 8 cosine 20t minus 25 degrees. And VC of t was 5 cosine 20t minus 165 degrees volts. So now you have to watch me suck at drawing 3 sinusoids simultaneously. So I'm pre-apologizing for that. If I were to plot these signals as a function of time, it would look something like this. So let's start with VA of t, which I'm going to do in red. So I have a small positive phase angle. So I know that this signal is going to hit its peak value a little bit before t is equal to 0. Okay. So I'm going to put its peak right here. So this curve in red represents my best attempt at VA of t. Okay. VB, I'm going to put in blue. We have a relatively small negative phase angle. So maybe something like this. Good enough. And then finally, VC of t is a signal with a very large negative phase angle. So I'm going to put its peak like right here. Something like that. So looking at this graph, I can say that VA of t leads VB of t and VC of t. So let me talk about what I mean by it. VA of t, our red curve, hits its peak value at an earlier point in time than VB, our blue curve, or VC, our green curve, right? So this one hits its peak earlier, so it's leading the other two signals. VB of t lags VA of t and leads VC of t, right? So because VB hits its peak later than VA, it is lagging VA. Because VB hits its peak earlier than VC, it is leading VC. Okay. And then lastly, we could say that VC of t lags both VA and VB because VC hits its positive peak at a time later than both of those other signals. Right? So looking at a time domain graph like this, it's pretty easy for us to see which signals are leading and lagging and all of that kind of good stuff. but it's a little harder for us to determine by what angle the signals are leading and lagging each other. So instead of looking at these in the time domain, my preferred method to do comparison is actually to look at them in the frequency domain. And so what I'm going to do is effectively, I'm going to take a snapshot of each of these signals at t is equal to 0, because I know that cosine of omega t at t is equal to 0 is just, excuse me, omega t is just going to look like 0, so I'm just going to have cosine of the phase effectively. So if I were to make a phase plot, okay, it might look something like this. So my positive horizontal axis represents 0 degrees. My positive vertical axis represents 90. My negative horizontal axis would be plus or minus 180 degrees. And my negative vertical axis would be negative 90 degrees. Okay. So I would represent VA by saying I need a vector of length 10 with an angle of 18 degrees. So something like this. VB, I need a vector of length 8 with an angle of negative 25. So somewhere in the ballpark of this. And then lastly, I need VC, which has a length of 5 and an angle of negative 165 degrees. So that would be somewhere over here. So let's talk about what leading and lagging represents on a phase diagram like this. So leading just means that our phase angle is more positive, and lagging just means that our phase angle is more negative. So if we measure, let me write that down. So to look and see if something's phase angle is more positive, we're going to measure counterclockwise. Okay. And to see if something's phase angle is more negative, we're going to measure clockwise. So if we wanted to find out by how much does, let's say, VA of t lag VB of t, what we would do is we would start measuring from VB. So that's our reference. We're comparing VA to VB. And because we're finding lagging, we would go clockwise around our circle. So we would start at VB and go all the way around to here, right? So let's figure stuff out. Okay, we're just going to break this down into smaller, more manageable parts. So this bit right here is just 90 degrees minus 25 degrees. This part right here is another 90 degrees. This part right here is another 90 degrees. And then this part right here is 90 degrees minus 18 degrees. And then we just add all those angles up, right? So 90 minus 25 is getting us from quadrant 2, or excuse me, 4 into 3. Add 90, so that takes us into quadrant 2. Add another 90, that takes us into quadrant 1. Add 90 minus 18. That takes to where we're trying to get to. 317 degrees. Positive, because we're just adding up the angles as we measure clockwise. This is literally the process for measuring leading and lagging using a phase diagram. We start from our reference signal, and then we go counterclockwise for leading, clockwise for lagging. Now, this process is 100% correct. Web work is a goof. And so what I mean by that specifically is web work doesn't know that, let's say, 360 degrees and 0 degrees and negative 360 degrees and 720 degrees all represent the exact same thing, okay? So when you're doing this on your web work assignments, you can do this absolutely correctly, and the web work will tell you that you got the wrong answer. All you need to do is add 360 degrees to your answer, see if that is what web work takes, or subtract 360 degrees from your answer and see if that's what web work will accept. It's just because of the way that it was coded and because it doesn't know that there are equivalent angles, okay? So if you follow this process, start measuring from your reference the second signal mentioned in the sentence to the first signal mentioned in the sentence. If you go lagging, it's clockwise, leading, it's counterclockwise, you are doing it 100% correct. Then just play around with the angle until web work starts yelling at you, okay? And by play around with the angle, I literally mean add or subtract 360 degrees. Okay. All right. I think that's enough out of me for today because we only have 13 minutes left of class and I want you guys to be able to ask questions about how to use a calculator. So I will stop ranting about math for today. Yes. Yes, let me. My bad. I need to put that up and then probably put up several others as well. No, I don't care what's new. Yeah, I think they have to legally be up by 5 p.m. today. Employers are required to get them to you by the end of January. Yep. Me too, so I can pay back my savings account for the vacation that I've already booked and paid for.
Where are you going?
Orange Beach, Alabama.
I've been there every summer since I was born.
My family always vacationed in like Perdido Key, Orange Beach. And so that's where my wife and I have just decided to go. So we always try to rent the exact same condo at a place called the Regency Isle. It's on the Perdido Key side of that big bridge or whatever. And there's like not a lot of phoenixes and stuff around it, which means there's not a lot of screaming terrible kids to hear me swear because I'm wildly intoxicated the entire time I'm there. So works out pretty great. Nope, can't do it. Will
Like the big one that has hot tub on every balcony. It's like straight up expensive.
so the unit that we stay in, or actually the place that we stay in, they have jacuzzi tubs in every condo. Yeah. Late August, so like right after summer classes end, and then I will come back like 2 days before classes start.
I'm like, they need to get some better days so I can be here because I have to be here.
If you guys do wind up going down in late August or whatever at the same time, shoot me a text. We'll go out for dinner or something like that. If you want to hang out with an old man and his wife,
You have to watch the mountains.
we'll see. How good is her memory?
Like the last two words back. And my mom had said that word in front of her, and she said, so, yeah, same on my mom.
All right, ICA number 18 is up now. I'm gonna go ahead and put 19 up so that I don't forget to do that, and then I will put the submission portals up here in just a moment. And then I know this is gonna sound asinine. Could somebody send me an email to remind me to put the rest of the ICAs up for the entire class? Because I should have done this literally 2 months ago, but I just keep forgetting to do it. Yep. Thank you. Yes. Oh, was an inevitability. Now that the test scores are out, there will be more. I don't think it will be nearly as much as other sections because our test scores have been higher than other sections, but there's never not going to be somebody dropping this class.
What was the average class?
Something, I can look at it in a moment. Let me finish doing this or I'm gonna forget. This is ICA number 18. Having to do with complex number stuff. So for class meeting number 21, I literally see ICA number 18. You guys not see that? Okay. Okay. Yeah, okay.